Hi, and just today we are going to work out on a problem which is based on the percentage conversion and the volume of the gas at standard temperature and pressure. So here we have our question. The gases entering a reactor contains A and B in the mole ratio of 1 is to 4. The mole ratio of these gases in the exit stream of the reactor is 1 is to 4.25. What volume of the gas in the meter cube at standard temperature and pressure must enter the reactor to produce 100 kilomoles of product C per hour? And they have mentioned the reaction, that is A plus 3 times B gives 2C. So first let's draw the diagrammatical representation. So suppose this is the reactor. Here we have reaction E plus 3 times B gives 2C, and here we have a product in the ratio of 1 is to 4.25, and the fade is in the ratio of 1 is to 4. So first what we are gonna do is, so let conversion of A be X, and by the definition of conversion we know that conversion is equal to moles of A reacted divided by moles of A fed. So if the conversion is X, then the moles of A reacted, and we have the moles of A fed, that is 1 kilomole of A. So moles of A reacted moles of A reacted is equal to X kilomoles. So now we know that according to the mole balance, if we do, so moles in should be equal to moles reacted plus moles unreacted. So moles in is 1 kilomole is equal to moles reacted are X plus moles unreacted. So moles unreacted of A will be equal to 1 minus X. Let's call this equation number 1. In very similar fashion, we know that from this reaction 1 kilomole of A is reacted with 3 kilomole of B. So if X kilomole of A is reacted, so if X kilomole of A is reacted, then how many kilomoles of B will be reacted? So this will be 1 into question mark is equal to 3 times X. So kilomoles of B reacted is equal to 3 times X. So from this mole balance, again we can write that moles of B in should be equal to moles of B reacted plus moles of B unreacted. So moles of B in is, the moles of B in is 4 kilomoles is equal to the moles reacted are 3x plus moles unreacted. So 4 minus 3x will be the moles unreacted of species B. And now from this reaction we can say that when 1 kilomoles of A is reacted, then we get 2 kilomoles of C. So when X kilomoles of A will react, then how many kilomoles of C will be formed? So this will be equal to 2 times X kilomoles of C will be formed. And now we know the proportion of the product, so it is 1 over 4.25. so this is 1 over 4.25 should be equal to our A in the product is the A unreacted, so this will be 1 minus x divided by the B in the product is B unreacted, so this will be 4 minus 3 times x, and from this equation we can calculate the value of conversion x. Let me take out my calculator. So this will be 1 over 4.25, which will be equal to 1 minus x divided by 4 minus 3 times x. So a conversion will be equal to 0.2. So if we put this conversion here, so moles of C formed is equal to 2 into 0.2 will be 0.4 kmoles. So now we can conclude that when 0.4 kmoles of C is formed, then 1 kilomole of A is reacted. Then if now they have asked for 100 kmoles, so when 100 kmoles of C is formed, then how many kmoles of A are fed? So this can be written as 0.4 into x will be equal to 100 into 1. So moles of A fed are 250 kmoles of A fed, and this will be 250 times 4 will be the moles of B fed, so this will be 1000 kmoles of B fed, because here we have the feed in the proportion of 1:4. So if A is 250, then B should be 4 times 250. So the total moles will be 1250 kmoles of total feed, but we need to calculate this quantity in volume. So we know that 1 kilomole of gas at STP occupies 22.4 meter cube of volume. So 1250 kmoles of feed will occupy how much volume? So this is 1250 into 22.4, so the volume of the feed will be equal to 28,000 meter cube per hour. So this was the way to solve the problem which are based on the reaction and when the feed is in the mole ratio of some percent. So thank you for watching this video.